So, hi, I'm Ian George. Thanks for coming to the slide version of a poster talk. I'm going to be talking about finite key analysis of quantum key distribution with characterized devices using entropy accumulation. This is joint work with Gilles and Thomas van Himbeeck, Fang, and Norbert Ltkenhaus. The archive number's at the bottom. It will also be at the end of the talk if you want to, learn more. So how do we motivate this work? Well, one way of looking at the general QKD protocol is the following sequential setup. So Eve constructs some joint state, rho an, bn, e. E she's going to hold on to. You can think of that as the purification space, and then she'll send the an space to Alice, and the bn space is to Bob. And then Alice and Bob are going to do this sequential protocol, which you can see what they're doing is they exchange some public information, which is this P register in each round, and they generate their local data xi and yi. So at the end, they have their local data xn through 1, yn through 1. Eve has learned some information about the data through these public announcements, pn through 1. And what Alice and Bob want to do is establish security. And so the way they do this is they perform error correction and privacy amplification. And by doing this, they either construct a secret key K that Eve doesn't know about, or they abort. And so why this is helpful is we can think of the general QKD protocol up here as being sequential, and the entropy accumulation theorem tells us that if we have a sequential protocol, we accumulate entropy in a certain fashion. And the application of the entropy accumulation theorem has actually significantly improved DI QKD rates recently. So the question is just like, can we do the same for device-dependent QKD? How much of an advantage does this give us? And the answer is yes, we can do it, and actually it's better than the previous best method, as we show. And so that's sort of our big result. And so let's sort of talk about how we prove that. So we can carve up our major result into 3 pieces. The first is we generalize the applicability of the EAT, specifically like it was not clear previously how you could, say, announce that you received the vacuum if there was loss in your system. And so we address that in our setting. We prove security from any entropies, which you could do in the device-independent setting. It's just no one's actually proven security from any entropies previously, and it turns out to be quite helpful for the key rate, so we want to stress it. And then lastly, we construct algorithms that give us near-optimal results numerically, which basically means that we get the best results possible out of the entropy accumulation theorem. And so combining all these things, we get a tight security proof, tightness up to the security proof method. For entanglement-based QKD protocols, that it's entanglement-based just has to do with the fact the entropy accumulation theorem seems to really only apply to entanglement-based protocols in general. And it's better, and our security proof method ultimately gets better rates than the best previous method. So that's really exciting. So let's talk about this in a little more detail. To understand this in more detail, we need to talk about the EAT in some more specifics first. So effectively what the EAT says is that like if you have a sequential protocol, then the secret registers, these SN through 1s, will generate a sufficient amount of entropy that scales as like this n times h and these correction terms. Notice that the secret registers are being conditioned on some public registers and also Eve's purification, and this has to be conditioned on some event omega. So you have some statistics that are telling you how this scales. And so the way we can think of it about this as being entropy generated is like you can think of this h as capturing how much entropy could be generated per round, because it's lower bounding this f of q for all q in your event. And this f is known as a min-entropy function, and basically what it tells you is the minimum entropy that could be generated asymptotically for any observed q in the probability simplex. So this is why it's like entropy per round. And the one condition for this that you have to satisfy is you need it to look like a sequential protocol, and what that means is you really need these Markov chain conditions, because these capture the notion of being sequential. And in the device-independent setting, this is like effectively trivial because all of the public announcements are like independent of the state. But in the device-dependent setting, we often talk about the state. So for example, I announced the vacuum, and so that tells you something about what the state was. And so we need to address this. And so what we prove is that the Markov chain conditions are satisfied if only subspace information is announced publicly. So since the vacuum is sort of a subspace of a quantum state, this holds for optical implementations, and so we can talk about proving security in optical implementations. So here we just consider BB84 with a spontaneous parametric downconversion source with loss. And so you can see what's going on is like we've plotted it for a couple of distances, and what's happening is as the distance goes up, the key rate goes down, and so it's not as loss tolerant as perhaps we want, but we know that this is the best the EAT can do in this fashion, given that we have a tight proof method. So that's the first result. The second is the security proof from Rényi entropies. So let's sort of just explain why this is a problem in the first place. If you apply the privacy amplification or the leftover hashing lemma in terms of smooth min-entropy as a standard, and then you want to use the EAT, then basically you have to use a bunch of chain rules in your security proof, and these chain rules will get correction terms due to this smoothing epsilon. But these chain rule, like this hurts your block length in the small, it hurts your key rate in the small block length. And there's no real reason to believe these like smoothing corrections are real, and we want good small block length key rates because that's practical for actual implementation. So we want to fix that. And so the way we fix it is we use the leftover hashing lemma that Dupuis recently established using Rényi entropies, and then we modify the entropy accumulation theorem slightly so that we can do our whole security proof in terms of Rényi entropies, and then we don't have these smoothing correction terms. And this actually turns out to really improve the key rate in the small block length. So the Rényi entropy is the red dots, and the smooth min entropy is the green dots. This is for basic BB84, but this is still, I mean, it's a significant difference in the small block length, which is what we care about. So this is exciting, and again, I mean, this isn't restricted to our setting, so hopefully other people can use it as well. And then the last thing we do is we establish near optimal numerical algorithms. So what does that mean? So again, the entropy accumulation theorem has this form where it's like round by round, and what basically the limit is how good of an H you have. And the way to get the best H is to get this best min-tradeoff function F, right? Because if your min-tradeoff function says that there's no entropy in your event, then you don't generate any entropy, but it could just be that you developed a bad min-tradeoff function. So the solution for that is that we first show that previous work effectively is getting the idea of how to construct a near optimal min-tradeoff function to first order. So by first order, we just mean that it picks the best H. It will get you the best H. But we actually go further than that. We construct a near optimal F that considers the second order term. So what this means is it gets you the best H, but it also considers this correction term that scales as square root of n. And so it might get you a better key rate in the small block length, which again is like the most practical setting that we care the most about. So this is really nice. And so actually, if we combine our near optimal numerical algorithms with our Rényi entropy security proof, then we actually get better key rates than the previous best general method. And the best general method previously was the post-selection technique, which scales badly in the dimension. So sort of intuitively, we would expect as d goes up, the entropy accumulation theorem would do better than the post-selection technique, but actually, even for small d, we do better. So here we're just considering two mutually unbiased basis protocol in some Hilbert space of dimension d. So if d equals 2, you can think of this as BB84, and then just think of this as generalizing BB84. And so what we see is as d goes up, the entropy accumulation theorem is doing better and better, but even at d equals 2, so in BB84, entropy accumulation is doing better than post-selection technique. So this is really exciting. This tells us like this is a good method. And then if you make d go up even higher, then you get bigger and bigger gaps between entropy accumulation and post-selection. But again, I mean, even at small dimension, which is generally what people do, we're doing better. So that's great. So just to summarize, we generalize the applicability of the EAT so that it can be applied to like optical implementations. We showed how to do security proofs from Rényi entropies, which should be useful sort of across the board. And we also developed near optimal numerics so that we have like the best method for applying the EAT. Like it's a tight security proof method. Yeah, so thank you. Again, the archive number is there if you want further information.